Okay, so let's get started. It's a great pleasure to have Devin Petersohn from Snowflake. Devin got his PhD in 2021 from Berkeley, the Rice Lab. He was advised by Aditya Parameswaran, and he had this really interesting idea as to how to bring databases and data frames together. They had an open source project called Modin, which the last time I checked had about 10K stars on GitHub and was used a fair amount, was really popular, caught everyone's attention in both the data science and the database world. And no surprise, they were recently acquired by Snowflake, where they're now bringing this AI ML world and databases together. And super delighted to have you, Devin, come and give this talk. Would love to have you return back at some point and give this talk in person, but we know you have a great excuse, having had a daughter being born just 2 weeks ago. So with that, a huge welcome to you to Carnegie Mellon, even though it is virtual, and the floor is yours.
Yes, thank you very much, Jignesh. The title of my talk is Beyond SQL Data Frames in the Database, and the whole goal is to kind of unify the data science and the database worlds, which have traditionally been very separate. So we are going to get quite into the weeds in terms of like technical details on data frames and that kind of thing. But I hope everybody will be able to take something out of this because the talk is kind of designed to talk at different levels for folks who like, various aspects of the data frames and database spaces. So first, though, a bit of an introduction. Thank you, Jignesh, for the wonderful intro. I was fortunate enough to get my PhD from Berkeley, where I got sponsored by a couple of fellowships, which actually let me kind of do whatever I want, and that kind of helped spawn Modin. So I call it out here specifically because without the support of these fundings, I may not have actually created Modin, and I may not be here talking to you today. So I'm very grateful for the financial sponsorship that I got during my PhD. Before that, I did my bachelor's at University of Missouri, and prior to that, I was in the United States Marine Corps. I have a fun little picture here of me meeting Joe Biden in 2012 when he was vice president. He came out. I was stationed in Hawaii. He came out and visited with us. He was very patient, and he was there for hours. And I couldn't imagine myself having done that. Yes, it's very interesting that I got to get a picture of me standing right next to him. It's not every day that happens. So, but yeah, so my PhD thesis was data frames. It was titled Data Frame Systems Theory, Architecture, and Implementation. Basically, my PhD was focused on like what is a data frame and how do we think about them? How do we think about building them? And how do we actually go about implementing them? And so I am gonna, borrow a lot of the stuff that we talked about or that I studied in my PhD, but there's a lot of new stuff in here too. So in general, the way the talk is kind of outlined, I encourage any of you to ask questions at any time. This isn't like a lecture or anything like that where I need to go through everything. But please feel free to ask questions at any time. So I'm going to start by talking about the problem, and I am going to go into detail about the problem itself and about the types of problems that data teams generally face in industry. Then we're going to talk about what is a data frame and go into the kind of formalism. After that, we'll talk about a pandas API for Snowflake, and then we'll talk about Snowpark, which is the Apache Spark API for Snowflake. And if you aren't familiar with what pandas is or what Spark is, don't worry, I will cover these, and you won't be lost, I promise. So I kind of want to start with this like really broad statement that is data and interacting with data has a syntax problem. The problem is that the syntax that you use or the API that you use to interact with your data depends on where the data is. If your data is in a database, you have to use SQL, and you have to use a SQL flavor that database speaks. If you want to use a different API, then often you have to move data. And this is a real problem, I think, because moving data is expensive. And often you're moving data from one system, which knows how to operate on the data in the way you'd like, to another system just to use a different API. And so this, I think, is a pretty significant problem because moving data is expensive, and it's often the most time-consuming and costly component of this. And when we tell people, or the world that we've created, I guess, it's not that we're telling people this, it's that like the world just kind of emerged in this way. Really, people have choices between two options. They either have to choose between their productivity or the computer's performance. And I'll talk a little bit more about why this is in a moment. So currently, everything is tightly coupled from the API to the execution. We see this in databases, we see this in data science libraries, and there's not really an easy way to move across this barrier right now, right? If you want to move things, if you want to use, let's say, a Python API here on the left, with data that starts in a database, let's say Snowflake, then you have to move data, right? And you have to move data into memory, and then you can operate on it, and then often that data just ends up back where it started, right? So you're paying to move the data, you're doing something with it, and you're putting the data back. And I mean, hopefully it's obvious why this is a problem, because it's extremely expensive. And a lot of organizations have kind of worked around these limitations by building systems that look like this. So when you start out in a laptop or on like a large workstation, you're usually using something like pandas, a single node tool, Python, to kind of prototype and explore your data. Then when you want to kind of start moving this into production, you move on to testing. That requires a rewrite. So you use a big data tool so that you can scale it. And then, for production, things need to be kind of rewritten again, and there needs to be a little bit of tweaking and that kind of thing. And to go from this prototype phase to production, we've seen it take more than 6 months, and there's a failure rate on the order of like 50%. So a lot of these things that are being prototyped are never actually seeing the light of day in production. They're actually never becoming useful because we have this huge breakdown in tooling. And I see this as a tooling problem. Now, the problems don't stop here either, because imagine that you run into a bug in production. So then you have to go back to the original writer of the code, who wrote in a different language than the bug kind of emerged in. And the whole process kind of starts over again. And so this is extremely frustrating. It's extremely frustrating for everybody involved, right? Because it's often different people who are doing these different phases, right? There's a data scientist who kind of understands the data, and they're operating at this smaller scale, kind of prototyping and figuring out what to do. And then there's a data engineer or an ML engineer who's kind of productionizing these things and actually writing these large pipelines that go into production. And so we are forcing people to choose the API they want or the execution that they want, because the things are so tightly coupled. And when we say that you have to choose between the API you want and the execution you want, really what we're saying is you have to choose between your productivity or your computer's performance. And by performance here, I mean either latency or scalability, whatever your company kind of requires. And so there's this kind of false dichotomy. I think it's a false dichotomy because I think that we can actually solve this. These are solvable problems, but it's a false dichotomy where you're forced to choose between the API and the execution or the performance. And if you choose a tool for the API, the execution gets chosen for you. But basically, you're optimizing for your productivity. And this is where a lot of data scientists live, right? They're optimizing for their productivity, and rightfully so. They want to be good at their jobs. And so it's important for them that they're able to do their job quickly and iterate fast. When we look at choosing a tool for execution or performance, the API then gets chosen for you. So data engineers often live in this space because they're a lot more familiar with and a lot more agile with choosing different APIs, operating in different constraints and that kind of thing. But generally, this is optimizing for the machine's productivity or the machine's performance. And so back to my original kind of problem statement, the syntax that you use to interact with data depends on where the data is. And if you want to use a particular syntax, often you need to move the data. And this is what we want to avoid. This is kind of the world as it is now that we want to kind of fix. Now, a lot of people will say, well, we should just have everybody use SQL. No, we should not. We should not force everybody into using SQL. We need a solution that works everywhere. And I will talk a little bit about why SQL isn't enough for a lot of data scientists later. But this, I think, is kind of missing the point. The point is not that we need to tell everybody what to use, or we need to be regimented in how everybody interacts with data. Rather, I think that we can create a solution that works for everyone, where people can be comfortable in their APIs of choice and interact with data in a way that's comfortable to them, but they don't also have to sacrifice execution and performance and these other things that the business might need. And so my big kind of conjecture here is that the next major shift in data systems is going to be the decoupling of API from execution. So this means that you can have the API that you want with the execution that you have, like Snowflake. And by allowing this, or by enabling this, you can actually give people both productivity and performance. Snowflake is massively scalable, and a lot of teams are using it for its scalability. If we can unlock the ability to let everybody operate at that scale, then I think everybody will just kind of elevate the field a lot more. And so at Ponder, which was my startup that got acquired, at Ponder we actually built a Pandas API on top of Snowflake, and basically we could just run Pandas API, which traditionally is limited to only a few gigabytes, on a terabyte, and it just works. And I'll talk a little bit about how and why. But at a high level, we basically had to build three components. We needed a low-level representation of how to operate on data, or kind of an algebra. We needed implementations of this algebra, like a compiler of some sort. And then we needed high-level language bindings for existing APIs to this algebra. And so how did we get to this conclusion that we needed to build these things? Well, we started from first principles, like everyone should, and we kind of thought about this from going back to first principles and actually thinking about the problem fundamentally. So looking back at the kind of landscape, and how everything is tightly coupled, there is no real ability to use a Pandas API, or excuse me, there wasn't a real ability to use like a Pandas API on top of these tools on the right, like on top of Snowflake. However, if we really drill down and think about what these tools are and what they do, then maybe we can start to reason about how we can start to map these APIs together. Okay, so I'll pause here for any questions, if there are any.
Devin, so I have a quick question which you can defer to later on. When you
Yes.
mean the Pandas API, do you mean the entirety of what you see in the Pandas API, or key interfaces to that in the API? Because often you'll have data science programs that will use Pandas. They might use the entire subset or rich subset that's available. And how much of that can you make transparent in this new scheme?
Yeah, so I do answer that later in the talk. I'm kind of teasing a little bit. So I'll defer this to later. And then if I don't answer it completely, then I'm happy to revisit.
Sounds perfect. We have another question. Prashant, you have your hand raised, so go ahead and unmute yourself and ask.
Yeah, just a quick question. I just wanted to know, so is this data frame extension towards like the SQL that is going on? So is it more like, can it also be extended to no SQL or any other infrastructure that is there? Or for the goal is to currently integrate the SQL side of things?
Yeah, so I'll defer this one too. But at a high level, I'll go into more detail. But at a high level, the IR, the algebra / IR level, IR is intermediate representation for those of you who don't know. This algebra layer, we just need to implement it, and it can be implemented in any of these languages. Now, whether or not those tools, like a NoSQL, let's say a NoSQL database, support everything in that algebra is not, that I don't know, right? I don't know if let's say MongoDB, right? If I don't know if MongoDB is going to be able to support the entirety of the algebra, but it can be implemented for those things that it does support, and so it is powerful enough in that respect to be able to do things like that.
Great. Back
Okay.
to you, Devin. Yep.
Okay, so we're going to be focusing on pandas and the Python ecosystem and kind of comparing data frames in like pandas data frames specifically to databases and arrays. I'm going to start getting into the kind of the deep details about what a data frame is. Um, and so when we look at pandas, for those of you who aren't aware, pandas is the de facto Python library for data cleaning, transformation. It is the data frame. It's often cited as the reason why why Python is so popular. It has more than 4.5 billion installs, which is mind-blowing. But that's because it's kind of this Swiss Army knife. So it's extremely flexible. It lets you, you know, mutate the data and everything and in every way that you need. And so it's just kind of become this standard for interacting with data. Now, Jignesh asked an interesting question. It does have more than 600 APIs, so it is massive in terms of the API. But that's just because of the flexibility that it enables. But it is a single node tool, and it's actually not only single node, but single threaded, which means that you can only use one CPU on your entire machine. And so you're limited to what you can fit in memory. Out of memory errors are common. It doesn't have a query optimizer, so you're kind of punished for writing bad code, which in general we don't want whenever we're talking about data manipulation. And so generally, like I mentioned previously, teams are fixing or solving this problem by adding another step, which is to translate this into something that is more scalable, something that kind of has more guarantees that they require. And that basically means that there's lost productivity on the team. There's 6 months of an engineer's time is an enormous amount of time to spend, and even then with a 50% failure rate, you're looking at a very expensive process for solving this kind of tooling problem. And so we're going to take a look at now kind of a nice analogy for how to think about databases versus pandas. Speaking to the database group in this context. So I hope you all will kind of enjoy this analogy. Professor Aditya Paramaswaran initially coined this, so I'm borrowing it from him. But so everybody here is familiar with databases and what a database is. And so for this analogy, I think it's helpful to think of a database as a Michelin star restaurant. The menu is curated. You have this nice tailored experience. Everything is kind of predefined for you, so you kind of know what you're getting, and everybody kind of gets the same thing. And so let's take a look at pandas now. If we look at pandas, pandas is a completely different data model. It's a completely different API, and it has all of these APIs, over 600 functions, like I mentioned. And if a database is a Michelin star restaurant, then you can think of pandas like a food court where you can kind of go and mix and match everything that you'd like. You can do something kind of crazy like mixing sushi with French fries. So there are all kinds of things that you can do with pandas, and it's just extremely flexible. And when we look at comparing these two in terms of convenience, with databases, you have to provide the entire query at once. Basically, this is the SQL problem. It's declarative, so everything is defined at the same time. Whereas with pandas, you're incrementally building up queries and you're inspecting intermediate results. Those of you who have written a lot of SQL, even like very long SQL, you'll know that it's very difficult to write these kind of complex SQL queries because it's difficult to debug, subqueries or query components and that kind of thing. So flexibility. Databases have strict schemas. They are defined schema first. You cannot start inserting data into a database until the schema is defined. With pandas, it supports mixed types. You don't need to define the schema up front. There's this kind of data and metadata equivalence it's just extremely flexible, and it can kind of gracefully handle a variety of things that the database just would disallow completely. And then versatility, in a database, it's select from where, and that's just about it. Whereas with pandas, there's more than 600 functions. So you kind of get this extremely flexible, and this is why it's kind of a food court, right? You can kind of mix and match different components of the data frame and kind of build up your query however you'd like, and it supports a lot more kind of real world issues that you might run into. So when we think about decoupling data frame APIs from execution, which is our whole goal, right? We want to give people the ability to use the API that they want with the execution that they have. If we're thinking about this from first principles, there's a whole host of problems that we need to look through. First, we're going to look at the data frame data model. Basically, what is a data frame? And then we're going to look at the data frame algebra. And the data frame algebra is what can a data frame do? After that, we'll look at parallelism and decomposition rules. This is like, how do we go about implementing efficiently these things that a data frame can do? In this talk, I'll touch a little bit on type system and the operator semantics. I'm not going to go into super deep detail. And then we'll talk a little bit about the implementation. So the first thing that we did was basically formalize the data frame. We wrote a vision paper in VLDB in 2020. And I was fortunate enough to work with a number of people on this that often it's difficult to get database professors to agree on things but having this many database professors involved and very involved was a big honor, I think. So but we did land on something that I think is extremely sensible, and the formal definition kind of came out as this. Now, I'm not going to read this to you, of course. It's in the paper, and I put it here just to show you that we have it. But if you're interested, if you're kind of more of a theoretically minded computer scientist, then I encourage you to go and take a look at it and read it. But I am going to break down a little bit about what that kind of formalism block says at a high level. So the way to think about data frames is that they have a certain number of kind of properties. So data frames are ordered, but not necessarily sorted. So this means that users can kind of produce their own order based on how they write certain types of queries, but that doesn't mean that it has to be sorted by a particular column or by a particular set of data. And this is true for both rows and columns. So often databases have the ability to, select the first column or something like that. In Snowflake, you can do that. In data frames, you can also select the 10th row, and you can't really do that in a relational database. There's also row column equivalence. So there's a symmetry between rows and columns. The data and, excuse me, the metadata that you have for columns is similar to the metadata that you would have for rows. So columns have names and rows also have names. You don't need to predefine the schema. So this means that you can kind of infer the types at runtime. And it's kind of no wonder that data frames are really popular in languages like Python, which support runtime type errors and don't require everything to be precompiled. So I think that this is kind of a key component of data frames because of the flexibility, right? And in the real world, we're often running into data that is kind of malformed. You might have a string value in a numeric column. Data frames will kind of gracefully handle this and allow that data to kind of be manipulated and fixed there in situ rather than having to have it be fixed externally and then pulled in. And then, type row and column labels. So you can basically, labels can become data, metadata and data are kind of interchangeable. And then indexing by label or by numeric index. So like I said, like selecting the 10th row or the first 5 rows. Or selecting the row that's named, December 21st, 2021 or something like that, right? So these are kind of the general high level properties of a data frame. Okay, I'll pause here for any questions.
I think we are good. We have a few questions, but we'll hold that. They're similar to the questions that were asked before. So, Devin,
Great.
you can keep going. Thanks for pausing that. Really appreciate that.
So, so I want to take a look at data frames from two perspectives, because I can say these properties, but maybe they don't mean anything in isolation. And I often think that it's really helpful to compare these to databases and matrices, basically. And these are the two things that data frames are most commonly associated with. I've heard a lot of people think that data frames are bad tables, or they're just like databases that are poorly implemented, or something like that. But in reality, that's not actually true. They have a lot of properties of databases, but they also have a lot of properties of matrices. They're kind of this hybrid of the two. And so if we look at this and we're kind of comparing these to a relational database, you can think of the data frame as kind of an ordered table that has row labels or row names. This is like the equivalent of the pandas index for those of you who've used pandas a lot. It has a lazily induced schema. So at Snowflake we support the kind of variant type, which is almost like an any type, and that type can then be kind of inferred to be something, or it can be converted to something that's a little bit more specific. And so a lot of databases have kind of started supporting not quite a lazily induced schema or a lazily inferred schema, but more of like a kind of a looser schema. It's becoming more common in OLAP databases. Okay, column names of arbitrary hashable type. This is a type where you can select columns uniquely. Column and row symmetry. This is, like I said before, they're kind of transposable, so you can convert the columns to rows and rows to columns. And then support for linear algebra operators like matrix multiply. Databases have a hard time with matrix multiply often. Yes.
Devin, on that last point, do you distinguish between data frame semantics and NumPy arrays, especially if you're in an application that is linear algebraic intensive, or you're unifying both of those concepts for the purpose of the way you're dealing with the semantics of data frames?
So data frames and pandas specifically actually does support like a dot product, and a lot of the kind of more matrixy things that you would want to do. I actually have an example later on in the talk about something that we converted to SQL that does like min-max normalization.
Cool.
And min-max normalization isn't something that you would normally think about in like a SQL context. It's very easy in pandas, but it's kind of complicated to do in a database. And so there is some, you are hinting at something which I do agree with. There is some goal here of kind of unifying these worlds. Data frames are kind of that object that unifies these two worlds. I'm not necessarily suggesting that we should directly be doing like complex deep learning and that kind of thing in the database or anything like that, right? But what I am kind of suggesting is that there are things that a database can do and is already set up to do. SQL is not always the right language to expose those capabilities. And so data frames kind of live in this world where it's kind of unifying these two kind of spaces, if that makes sense.
Got it. Yep. Thanks for that clarification.
Yeah. No, it's a great question. It's a great question. Okay. And then if we look at this from like the matrix perspective, or from like a linear algebra perspective, a data frame is basically a heterogeneous matrix-like data structure that has support for numeric and non-numeric types, column and row labels, and support for relational algebra operators like a join. And you can't really do a join in a matrix because what does that even mean? But there are it is kind of this unity of the two, or this kind of hybridization of the two. And with that comes a lot of power. Okay, so now at a high level we know what a data frame is. We've kind of defined that. Now we're going to look at what a data frame can do, and we're going to dig into the data frame algebra a bit. And defining the algebra is very important, because it gives us a low-level representation to kind of think about and move on to our further steps. So there's more than 600 operators in pandas. I've mentioned this a few times. Pandas has a data frame and a series. Data frame is a two-dimensional object. Series is a one-dimensional object. And then it has a bunch of these kind of convenience APIs that operate on data frames and other objects. And with data frame algebra, what we were able to do is we basically took those 600 functions and mapped them to 15 operators. And these 15 operators, you may be asking, like, how did we kind of derive these 15 operators? Well, it was I don't know if there's any tricks to this or anything like that, but it was a lot of hard work basically, and a lot of kind of like digging through API by API and seeing how we can reduce them. I don't know that there's a better way to do it, but in doing that, we were able to actually comprehensively say, that and confidently say that these are the kind of minimal set of operators that we have. And the interesting thing about all these operators is that they can be applied on rows or columns. And generally, if you're talking about applying operations to a relation, you're mainly talking about row-wise operators generally. So, for example, you can do a filter along columns that is based on some column predicate. So let's say I want to filter out all columns that are more than 20% null values. So in SQL, that requires two queries. You have to do the query to figure out the number of non-null values, and then you have to take that out of the database and then use that as a projection in your following select statement. In a data frame, it's all just one query basically. And so hopefully this kind of portrays the power of data frames and data frames as a language for interacting with data. Okay, and if we break these down further, we have the ordered versions of relational operators. And by ordered, we mean that given an input order, there's a deterministic output order for each of these operators. We have MapReduce style operators. These are things that most databases support anyway. We have a lot of metadata manipulation operators, metadata querying operators. This is a little bit trickier in a lot of databases because metadata is typically like a completely separate component and often used for things like query optimization, and it's not always exposed to the user in a way that they can query it. And then we have more linear algebra and order-centric operations, things like transpose, concat, which is kind of a union-like or a union-all-like operator, and mask. And so this basically tells us this middle layer that I was talking about. So I talked about we built this system that kind of has three layers. The first thing that we needed to do was actually figure out this middle layer, which is the algebra. Now we have that. And so next we took a look at how do we parallelize these? How do we kind of decompose these operators into smaller operators that we can use to operate on partitions of the data and start to think about scalability of these operators. So we wrote another paper in VLDB in, I think this was 2021. Yes, 2021. I'm sorry. Timelines always kind of tend to blend together. So I apologize about that. But and in this paper, we kind of discussed the like, how do we, now that we have this algebra, how do we think about parallelizing it when things can be operated on column-wise and row-wise and all of the new kind of challenges that come with data frames specifically. So the the goal here was again to kind of define some general rules that we could use, similar to how we drilled down the algebra. We wanted to drill down parallelization rules and define some rules. So basically, we built this taxonomy of parallelization, and I'm not going to go too much into detail on this because it's not totally applicable to the SQL to like mapping pandas to SQL. It is relevant in understanding kind of the limitations of these mappings and the challenges that you might face because there is this existence of like a column-wise decomposition and that kind of thing. So if you're interested in this, I encourage you to kind of check out the paper and take a look at it. It's very interesting if you're into like distributed computing and thinking about things from that. But the taxonomy at a high level is basically we have operators that can operate cell-wise, and this is like you want to convert every value in the table to a string. Let's say you're kind of going crazy and you want to do something like that. That would be an example of cell-wise. But cell-wise is by definition also row-wise and column-wise. And so if you're operating on these operators in these ways, we built this taxonomy basically because in general, we want to avoid data movement, data shuffling in a distributed system. And when you're talking about row-wise versus column-wise, some data movement does have to happen in order to move between the two of them. And so if we can, so basically that was the kind of general goal. But anyway, hopefully that piece of it made sense. But I don't want to spend too much time on this because it's not directly relevant to kind of data frames in the database. But I do think it's important, and it is a key part of kind of thinking about how to implement a data frame. And so the first implementations of the algebra were actually in general purpose distributed systems. And so from this, we were basically able to build some implementations of this algebra. Okay, I'll pause here. I'll pause on this slide. Any questions?
I think we are good.
Great. Okay. And so next, the kind of type system and like semantics of each operator. These are things that we also went pretty deep into and looked at. And these are important because it's important to databases have their own type system. So it's important to understand the type system of a general purpose data frame implementation so that you can map between the two type systems. That's a challenge in and of itself. And then, things like order semantics and metadata and how metadata is manipulated and inherited. These are also important because these aren't things that the database natively provides for us, right? The database isn't going to give us order. We're going to have to basically define an order. So these are things that we looked into in deep detail, and in the papers you can kind of get a good idea of exactly what all the requirements are for these for implementing a data frame in terms of like each of these operators. Okay, and now that we've kind of looked at all these from first principles, we can start to look at the implementation. So at this stage, we know what a data frame is. We know what operators it supports or what it does. We know how these operators map back to pandas because we did our homework. We know how to handle data frame types, and we can decouple the logical and the physical order. This is the order semantics that I was talking about. We are able to decouple the logical and physical order from each other, and we also know how to maximally parallelize each operator. Okay, and that gets us basically our kind of 3-layer system with that I was mentioning earlier, and that 3-layer system happens to be Modin, which is the project that I started as a PhD student. It has been it's used by a number of organizations, and it's been contributed to by several people, and it's not solely my work. I don't want it's been a big collaboration across a number of people. But in general, the goal for Modin was to be a drop-in replacement for pandas and perhaps even more languages in the future. And so if we look at the kind of three-layer architecture that I've been showing this whole time, pandas is basically at the highest level, and pandas is translated into this data frame algebra that Modin implements. And then from that data frame algebra, we can implement it on Ray or Dask or even Snowflake. And this is what we did at Ponder is implementing it on databases like Snowflake. And now I'm a part of Snowflake, and so we're working on integrating the work that we did. So if there are any questions about that integration, I don't know how into detail I can go because I'm not allowed to talk about anything that isn't public yet. But I will say, stay tuned because there's a lot of really, really interesting stuff that's going to be coming out, in the coming months and so on. So I do think at this point it's important to talk about what the formalism actually gave us whenever we're looking at the implementation. So when it comes to the data model, we get to kind of expose the feel of pandas without the execution limits. So pandas has heavily tied its API to its execution, but if we can decouple those, we can actually start to think about optimizing without the limits of the original execution. This also means that we can emulate the data model in other terms. And I chose the word emulate here very specifically because we don't need to actually fully implement this data model. As long as we can give the kind of look and feel of it, that'll be good enough for 99% of users. And then when we talk about the data frame algebra, I think it's really important to think about a smaller surface to implement. 600 operators, mapping those one-to-one to every system would be an untractable problem, right? We can't have pandas on every single database if we have 600 operators mapped to K databases, and it's just going to be kind of unfeasible. And this algebra also lets us map these lower level operators to other systems. And so I do want to focus on these two because this is what we did at Ponder. And I can talk a little bit about what we did at Ponder in terms of the mapping from pandas to Snowflake. And so things that are simple in pandas, right? Something like min-max normalization, it's more of a statistical thing that you would want to do. It's this one line of code here where you subtract the data frame from the min of each column, and then you divide that by the max of each column minus the min of each column. And it's one line of code in pandas, but it basically becomes 300 lines of code in SQL. This is because SQL just is not the right language for expressing these types of computations, right? It's possible to create, SQL keywords or constructs in SQL to be able to do this, but there are joins, there are cross joins going on here when it comes to actually implementing this particular API. And if you look closely, you'll see things like row labels are tracked in here, and the order is tracked in here. And so yeah, there's
Evan, a quick question. Is this because the translation from the underlying algebra to SQL is just composed without getting optimized? Or is this intrinsic
partially
nature of the problem? Okay.
so there are certainly ways to reduce this by a bit. There are a lot of places where things can't be reduced because there is a lot of code in here that is required to track order and to maintain order. Even like the data frame originally had an order, and so we need to preserve that order throughout the query. And each of these, when you're subtracting each value in a data frame from that value column's min, if that statement made sense.
Yep.
You have to do a cross join with the min, right? So each row needs to basically have access to its min. So there are probably ways to compress this a bit, but there are multiple joins that have to go on for this to happen just because of the nature of how you construct SQL, right? So this subtraction is a join, this division is a join, this subtraction is also a join. So the joins themselves aren't really all that expensive because you're just kind of cross joining with a row, right? And that's relatively cheap. But the language itself, that SQL as a language, kind of just isn't really that well. It's not that well suited for queries of this type.
That makes sense. Thank you.
And so the whole goal, remember, is to kind of allow people to have the same API, but not have to shuffle data around, not have to pull data out. And one good example of this is on this 150 million row data set. It's actually two tables that started in Snowflake. And through this, we were able to save over 2 hours of time. And you'll see that the majority of the time is actually spent on pulling the data out of the database, and also the join. Well, databases are great at joins. But also, if we can operate on the data in place, then we're going to save, several hours of time. And, I at one time I did the math on how much this costs, and it was, roughly less than $1 in terms of like Snowflake costs, right? So that's not official or anything, but the I mean, I would spend $1 to save 2 hours of my time. I don't know very many people who wouldn't. So this is just something that I think it's one of those things that just should exist, I think. And this I think is a good example of how we can save tons of time from the way that things are currently done in the status quo. So looking back at the data frame formalism and like how I map these to databases, right? I kind of went through these relatively quickly in terms of like the properties and what a data frame is and comparing that to a database. But there are a lot of things here that actually map to Snowflake very, very straightforwardly, right? It's something that we can either, have as, the data frame, the Python client can kind of track some stuff, or maybe we just compose the query in a certain way. There are things that are quite straightforward, but there are also things that are very difficult. And I wish we had, maybe 2 more hours or 3 more hours to kind of talk through all of these challenges. And some of these aren't completely solved. They weren't completely solved at Ponder, and so there are a lot of existing challenges, and there are a lot more challenges than just what I talked about with the data model, right? Because pandas and data frames aren't used in isolation. They're used as a part of an ecosystem, and the language differences between pandas and Python and a declarative language like SQL, that raises some interesting challenges, interesting difficulties. And so I threw up a list of kind of the challenges that we faced, the challenges that we wanted to solve in terms of like the actually making this experience a native experience, making it feel like you're actually in pandas and that you've never left. And so there are a lot of these challenges that are interesting and that are probably paper worthy if I ever get the chance to write a paper about them. But okay, so we're going to shift gears a little bit from the kind of pandas space to talking more about the big data space. Before I do that, does anybody have any questions about the pandas space?
I'll ask this now. Alec Dara Abrams from Berkeley Fire Safe Council posted on chat saying, could you comment a little bit about the connection between this and whether the data frame notion in pandas and the R notion of data frames, it differs slightly?
Oh, yeah.
Any thoughts on, is there a way to bridge that gap, or this is just purely targeting the Python ecosystem?
Yeah, so the algebra itself is enough to also support our data frames. So part of the work that we did was actually trying to figure out who created the data frame first, right? Where did it come from? And it actually emerged from the programming language S, which was developed at Bell Labs. And it in the late 80s, early 90s, the data frame was basically added as a feature. And then R is the open source version of S, basically. And so R got the data frame too. And so you can kind of think of the data frame as being this kind of like S and R originated structure. Now, we were very deliberate in how we define the algebra, and it can support the things that you would want to do in R. It's a lot harder to validate that because R is more of a functional language, and you don't really do operators on the data frame. You more pass the data frame to functions, and those functions kind of manipulate the data frame. But everything here that we've defined would also be relevant to R. And that was definitely a key goal. I'm mainly focusing on Python and pandas because of its ubiquity and to kind of keep the talk focused. But we definitely call this out in our papers. So happy to kind of chat more about that.
Wonderful. Thank you.
Okay. Yeah, so I talked a bit about the panda space, this kind of like starting in a single node. There's scalability issues, but there's this whole other world where people are using big data tools. They're using these large scale tools to kind of put things into production, and very often this is Apache Spark. And so what do we do about Apache Spark workloads, right? Our goal is to allow people to use the API that they would like with the execution that they have, Snowflake. And so if we're thinking about the big data ecosystem, how do we think about Apache Spark workloads? And so some of you may not be familiar with Apache Spark, so I'm just going to very briefly go over this. Apache Spark is it's an open source data processing engine that emerged from Berkeley, from the Amp Lab, that is used to process data across a large number of computers, a cluster basically, using programming constructs. It has a variety of different objects. It works in a variety of different programming languages. We're mainly going to be focused on Python, but it also supports R and Java and Scala. And in general, programmers are using Spark to query their data, analyze their data, and generally transform their data. Of note, though, Apache Spark has a data frame. And so the way that I like to think about Apache Spark data frames is that they're kind of relational data frames. They basically have a relational database data model. I used to be a lot more opinionated about this, where, as an academic, we're like encouraged to be very opinionated about everything. But in general, like the relational data frame construct is basically allowing you to have this kind of data frame language on top of more of a relational database kind of structure on the back end, if that makes sense. And if we look at what Spark supports when you compare it to Pandas in terms of like the actual data frame features that I've called out, you'll notice that Spark doesn't support order, it doesn't support eager evaluation, it doesn't have row and column symmetry, it doesn't have a lazy schema, but it does support these relational operators, the map operator, the window operator, things that a database would generally support. Transpose is unsupported, and a lot of the metadata operators are also not supported. And so you might be thinking, well, why don't we just tell everybody to use pandas, right? Because like, why would anybody use Spark in this context? But remember, our goal is to allow everyone to use their API of choice. We do not data frame shame. We want to allow people to use their API of choice with Snowflake execution effectively. And so when we went about solving this problem, we basically built Snowpark Dataframes. And Snowpark Dataframes, the Python version of Snowpark Dataframes, is basically focused on enabling scalable processing of Snowflake using the Python language. And it's intended to be a PySpark-like, PySpark is the Python version of Spark, a PySpark-like API that uses basically Snowflake SQL as a processing engine. And in general, Snowpark started with Scala just like Spark did, but when it comes to Python, we're working on basically having good parity with Snowpark's Scala API and being consistent with PySpark API semantics. And in this way, we want to basically also support, the Python extensions from PySpark and integrate Python UDFs and that sort of thing. One of the non-goals, though, what we don't want to do is support a pandas-like API because PySpark has its own API, and so our goal is to basically support those users. And so if we look at Snowpark's architecture, in general, there are kind of 5 phases of a query lifecycle, right? So a user can build up a query, and once they submit that query, Snowpark's API is basically compiling that query as they're building it up, and then when that query gets executed, it moves through the Snowflake Python connector over to Snowflake, which does all the processing and then returns the result. So it's a relatively simple architecture because Snowflake is doing a lot of the heavy lifting in this case. And so comparing Pandas data frames with Snowpark data frames, I think is kind of it's a good idea to do since I spent so long talking about Pandas and this sort of thing. So Pandas is ordered and Snowpark data frames are unordered, similar to Spark. And the goal here again is to give a lot of the same guarantees that you get with Spark. So Snowpark data frames also, though, does not have the overhead of maintaining order, and there is an overhead of maintaining order when it comes to Pandas. Snowpark's data frame is also a lot closer to SQL, so Pandas users might not find it as friendly, and so things that might not feel intuitive, like doing like df.sort, and you sort by a column, and then you do a filter afterwards, right? A normal Pandas user would assume that at the end of this, that df1 would be sorted, but df1 will not be sorted. Almost certainly the query optimizer is going to completely ignore this sort because that sort is not applicable to the end result. And so where you actually put the sort in this case does matter a lot. And one other key thing to call out is that Snowpark does not have row labels and the kind of metadata and data equivalents that Pandas has. Okay, and then I wanted to also talk a little bit about lazy evaluation in Snowpark and how the API is used. So in general, you can build up these queries and they can be as long or as complex as you'd like. And there are certain keywords that trigger execution in Snowpark. And this works exactly the same in Spark, just as you would expect. So you can kind of connect to a table, and then you can project some columns. You can do some filters. You can do a sort. And then at the end, when you do the collect, that's when basically the SQL statement gets created. And this is the kind of SQL statement equivalent that you would have. Now, one interesting feature that Snowpark has that Ponder did not have is the ability to kind of optimize this SQL and create more of a compressed SQL. That's definitely very helpful because some of the challenges that we've had are related to complex SQL queries. If you can build up an arbitrary amount of statements, then you can imagine that getting kind of very complicated on the server side for actually like parsing these kind of extremely complex queries. And no human is going to write a query as complex as something that generates SQL. That's just not how things work. So there are some challenges that we're working through on that. But if we kind of look at the Snowpark architecture when it comes to this query, the query is not actually sent through to the Python connector until one of those execution trigger words, like the collect, is actually called. And so in that way, we can do some client-side optimization in addition to the server-side optimization that's already going on as a part of the SQL execution. And so there are a lot of similar challenges, and a lot of the learnings that we had at Ponder also directly translate to learnings that we share at Snowflake and that sort of thing. But there are still really interesting open challenges around, materialization of intermediate queries and how do we deal with queries that are, arbitrarily complex and that sort of thing. And so, I hope that I can kind of inspire you all to think more about data frames and to think about these problems. And I would love to see more data frame implementations and more of these types of things, because I do think it's an incredibly interesting space, and I think that's understudied as well. So going back to my kind of organization diagram here of like how a lot of organizations operate. If you recall, our goal is to decouple API from execution. So even if users are in pandas and they're using pandas on the small scale and then using Spark or some other big data tool at the large scale, the goal is basically to have that data stay in Snowflake and allow users to get all the benefits that they've had from all the investment that their company has made in the security and the governance, to basically get that through the whole entire data lifecycle. Okay, so I'm gonna kind of wrap up in summary, and then I'll answer as many questions as we have. We covered a lot of material, and we kind of the talk was kind of very, very wide ranging. So I kind of want to do a high level summary really quick. So data frames are not databases nor matrices. They actually have properties from both, and they kind of are this interesting hybrid that gives them a lot of flexibility. The key takeaway that I want you to have is that we can decouple API from execution with the right architectures, and if we have the right constructs, and importantly, that is the formal data frame data model and the algebra that I was talking about. Because the data frame kind of encompasses a lot of what you would want to do in databases and also in matrices, it's kind of this nice hybridization that allows us to express computation and express data computations in a more general way. And then we can kind of map those to SQL or to, we can implement them in systems like Ray and Dask that Modin supports in the open source. Snowpark and Pandas both are also able to be APIs for Snowflake. We talked a bit about that too, and we have options for programmers who prefer one over the other. There are a lot of people who don't like pandas. I talked about how great pandas is, but a lot of people actually don't like how flexible it is, because it's so easy to kind of harm yourself accidentally when you're interacting with the data in not quite the right way. So in that respect, there are a lot of people who like Spark because it doesn't have the same flexibility. So the whole goal here, though, is to give options for users who prefer either. And the last thing that I'll say is that there are a lot of deep technical problems in data frames, and it's a really exciting time to work on data frames. I wish I had a twin that could also be working on data frames, but we're limited to the amount of time in a day. So yeah, but anyway, I really appreciate the opportunity to come and give this talk, and I'm happy to take any questions now.
It's fantastic. I'm just going to clap for everyone over here, and people can use the virtual reaction if they need to. That was a really nice talk. I'll see if people have questions, and I do have a couple, but I'll see if someone wants to go first. So I'll ask, you have this really nice algebra. Of course, you're at Snowflake, so you're going through all of these 600 functions that you've mapped through this layer. But this is generalizable in the sense that if you had that abstraction, you could potentially port that relatively easily to any other database system, because ultimately they're just generating, seems like for each of those functions, some SQL code, and SQL dialects differ, but I'm guessing you're using probably the least common denominator and the common core that's probably fairly portable across databases.
Yes. So at Ponder, we did support a number of other databases, DuckDB, Postgres, Redshift, BigQuery. all of those. So we actually started with supporting Snowflake, and the other database backends were not fully mature. But you're completely right. Like we at Ponder, we initially built it to be kind of a general purpose everything for every database backend. The interesting thing about being at Snowflake is that you know, we can influence the backend, and we can actually optimize the backend for a lot of these things. So can't talk too much about that, but there is I think there's an opportunity to make to create a really compelling experience with everything kind of fully integrated.
Yeah, no, that makes sense. If people have a question, just raise your hand and then I will call you out. You can unmute yourself and ask directly. I'll ask one more question, which is you don't necessarily have to translate because of the mismatch between the data frame API and SQL's limitation. You talked about several of them. You don't necessarily have to take a pure SQL approach in the compiler to generate pure SQL. Uh, is there advantages to using Snowflake scripting language and embed SQL, but mix declarative and imperative? Because at the end of the day, the API doesn't care if you can get a more efficient execution that way. Would it make sense to do that? Have you tried some of that?
Yeah, and there are so this is a great question. There are a number of APIs which are best done as like a UDF, a Python UDF in the database. In general, SQL is the fastest way and the most efficient way to interact with the database. So in cases where there is a clear way to do it in SQL, to do any operation in SQL, that's how we'll do it. One good example of this is like is null, right? Almost every database lets you check if a value is null, and so does pandas. And so in that sense, we would want to generate SQL because that's going to be the most efficient way of operating on it. When you do UDFs or when you these most of Snowflake still uses just SQL. There isn't a faster and more efficient way, but there are like internal things that we can do in terms of like Python UDFs and that kind of thing that
And I was thinking mostly in terms of some of the components, especially the column label components and manipulation of that. That's super hard to do in SQL. You have to reach out to the metadata store and do manipulation in that. Do you try to be a purist in SQL at that level, or go a little bit below the covers and basically get that manipulation done a lot more efficiently?
Right. So some of these were client side, like handled on the client side, basically. So the database maybe isn't aware that a column is the row labels, right? That would just be something that we would have in our implementation of the data model. And so in that sense, there's a little bit of kind of client side work. And when I say client side work, I mean like on the user's machine, there's some metadata that we're caching maybe. If you want to do a query on metadata, perhaps that can be done on the user's machine without having to go and fetch results from the database or without even needing to get the database involved. And so most of what we optimize for is cost to the user, actually. And in terms of like not spending all of their Snowflake credits on a single query or something like that, right? It's Pandas, as I mentioned, is kind of, it's very flexible, but it's also easy to shoot yourself in the foot. And so there aren't guardrails around Pandas itself, but at Ponder we created a bunch of guardrails in order to avoid this kind of shooting yourself in the foot. So but to your question, like the metadata and a lot of those components were handled outside of the database.
Got it. That makes sense. Wonderful. I think I don't see any other questions. So with that, we'll thank you one more time, Devin, and really appreciate you taking the time to come and talk to us. And hopefully we'll see you on campus sometime in the near future. Thank you.
Thank you.